So to wrap up today's lecture, let's just have a look at some real work that we at the University of Auckland have been involved with. So the first one here is behavior of continuous concrete filled steel tubular columns loaded concentrically in fire. I just add at this stage, this is just a bit extra. So it's not examinable, but it may help some of you put some things into context. So this is a paper that Charles Clifton and I got involved with, and we did some research to understand the behavior of concrete filled steel tubular columns. So if you look around, as you walk around, you'll probably see a lot of columns, tubular columns that we've just described and that we've just done some calculations on. So if you walk around your Westfields and other shopping malls, you'll probably see a lot of these. Now, you may or may not realize that steel sometimes has a lot of problems when it comes to fire, because steel suddenly loses strength. There's a sudden loss of strength with steel when it reaches a certain temperature. So there's always problems with steel. One way which engineers can get around this problem with steel is to fill the steel columns up with concrete. So filling it up with concrete, not only do you get a much stronger column because you've got steel plus concrete acting together, but the concrete can actually help a lot when it comes to taking fire load. So this is some testing that Charles and I got involved with, and the idea was to look at their behavior under concentric fire. So in these things here, we were loading the column right here, right at the centroid, which would be right at the center where these points would meet. So it's a concentric load as applied to an eccentric load. So an eccentric load is anything loaded slightly off away from the centroid of the section. So this we got it tested in India. So this is the column. This is the column that's being tested, and this is the furnace. So outside the furnace, it would gradually increase in temperature. Testing is probably the only way in which you can really be sure as to how something behaves. And for reasons that I'll explain a bit later, in the actual test, one end of the column was fixed. So that would be the boundary condition. One end of the column was fixed, and then we can see that the other end of the column is free, okay, or is a pin. So here, one end of this column was fixed, and the other end was pinned. So here is the furnace, and then this is the temperature. So the furnace is controlled as the temperature of the furnace is completely controlled, and this is known as the standard fire curve. So the red one here is known as the standard fire curve, and then to see how well we're able to control the temperature, it obviously will not be exactly the same because we're just trying to balance it with the temperatures, but you can see that the temperature of the furnace was pretty similar. The temperature of the furnace is the blue line, is pretty similar to what's known as the standard fire curve. So that would be the pin support, which you can see there. So that would be the support that we showed here. So that would be equivalent to the pin support. So you can see there's a roller down here to be the pin, and then down here right at the bottom that would be the fixed support, and then down here there's a load cell. So you might be wondering why we have one end fixed and one end free, and the reason for that is when you've got multi-story construction. So that's a multi-story frame, and then we'll just say that one is down there. So we would say that end would be the pin one, and there would be some fixity in that one there. So it's good when you do test, not to test it pin, but to test it fixed pin, because that's a more realistic loading condition. or that's a more realistic real condition which you would get in a real building structure. So that was a real building structure going on for more bays like there, and you took let's say you wanted to take that member out and you wanted to do a test. So that end would be the pin end, and then that end, since there's some fixity there would be some fixity there. So that's why we're testing fixed and pinned. And then these are the load cells. And then if we go through the test, concrete obviously inside, and then here is the reinforcement, which you can show here. And then we would have measured the strength of the concrete that goes inside our square hollow section, or our hollow section, our steel hollow section, into which we've applied the concrete. And then we would have stuck some thermocouples within it, so that we know exactly what the temperature is throughout the core. And then here are the experimental test results. So you can see sudden failure. So we increase the temperature and then suddenly sudden failure. And then once you've got the sudden failure in our different arrangements, so we tested one column with plain concrete, one column with the reinforced concrete, which you can see here. So that would be the reinforced concrete, and then a third one using some new material, which would be a fiber reinforced concrete. And so you can see the sudden drop here, or the sudden loss of strength, which you can see there, which is what we'll be learning to calculate. So you'd probably recognize that shape there. That looks like the pin, and that looks like the fixed, which you can see from the conditions. You can see the sudden buckling occurring. So if you look at the displacement plots, suddenly there's a loss of strength. So the column is quite happy, it expands, and then suddenly there's a big loss of strength. So you'll be learning in Civil 250 how, once you know the load at which the strength is lost, how you can do a safe design. But you can see a sudden loss in strength, pi squared EI over L squared. And there you can see the buckling shape, and there you can see the buckling shape there. And then after that, take out the concrete and just have a look at how it behaves. Here we have all the temperatures to show which temperature it failed at, and what's known as the load ratio for the fire load. And then from here we would have some conclusions. So you can see within the conclusions we're using terms like effective length factors, and we're using terms, or effective length factor, and you can also see, probably I just saw it, we use the term slenderness. There's a term slenderness somewhere here, which I can't, slenderness here. So all the terminology that we've been discussing just now in the last 3 lectures, that all comes up when we do proper experiments and try to understand the behavior of steel tubes under fire. So this is a different bit of research that we again did at University of Auckland, and this one looks at the behavior of cold formed steel channel sections under compression. So this is done in our laboratories here. So here we see a channel section. So if I drew out the cross section of the channel section, the cross section would look something like that. And you can immediately say that when we do our calculations on this, because it's so thin, because it's very thin compared to the overall dimensions, we would probably, and we did use thin wall theory in terms of the calculations, because it's a lot more laborious effort to use thick walled theory. So here we're using thin wall theory when we calculate the cross section of the specimen. So down here we can see some different cross sections, and you can see indeed it's very thin. The section is only probably about 2 millimeters thick, if not less, compared with the overall dimensions, and you can see what's been tested. This test here, when it is tested, that would be the cross section. So obviously the same cross section down here, and then that would be under axial load as we've described. And what we're looking for in this bit of testing is the effect of openings. So you've probably seen as you walk around that there are numerous openings in your steel members, and openings are very important. Obviously openings reduce the strength of the members, but openings are important so you can put your electrical services through. So they're very important to include both for beams as well as columns, so you can put your services through it. And as a result, in a 10-story building, you're probably saving 1 story by having your services going through the section rather than going outside the section. So if we did a sketch of a multi-story building down here, so if we did it like that, so if you can put your services through the beam instead of underneath the beam, eventually you're going to be saving 1 story if you build a 10-story building, which is not bad, which is why a lot of sections have openings in it these days. So again, careful measurements of the specimens can be seen here. Now this thing here, the shape of that is a dog bone, so hopefully you can see that down there. So from the steel we cut out the dog bone, so that's known as a dog bone, and then this thing here is tested in well, this is known as a coupon. So it's known as a coupon, so you might hear us use the word coupon test. So we cut out a coupon, so the coupon could be cut out from, say, we could be cutting out a coupon from, say, here, or we could be cutting a coupon out from, say, here. So we take the coupons out, and then we've got machines in our in the laboratory where we put the coupon in, and then we just extend it under tension, and then from there obviously you're going to get your stress strain curve. So you get your stress, and then you get your strain, and then the stress strain curve will look like that, and then that point there is fracture or rupture down here. So the initial gradient there would be E is the Young's modulus, and E, if you stuck an extensiometer, which is some magnets attached to it, you can get a fairly good accurate reading for what E is. And then from here you would know what the yield stress is, and then you might also want to know what the ultimate stress is before it ruptures. And so here you can see the stress strain curve. So I know in Civil 250 Charles will be talking to you about measuring the Young's modulus, which would be the gradient there. For steel, as we've said, a good number is about 200 times 10 to the 3 newtons per millimeter squared. Sometimes 210, but it doesn't really range too much. And that point would be the yield stress. So that point there would be the yield stress. There's a short plateau, and then it goes up here for the ultimate stress. When we do column buckling calculations, we're only interested in the yield stress because once it's reached the yield stress, it's got 0 strength. So after that, we would say that the column has failed. So when you so once the stress has reached the yield stress in the column, it can really take no more load, and it becomes unstable or it becomes a mechanism. Anyway, here are the coupons that we've extracted, and then down here you would see for the different thicknesses we considered, we've tabulated the yield stress, which is about 300, and we've tabulated the ultimate stress, which is just under 400. So coming on to the test, so here is the experiment. So universities do these experiments, and then these experiments, the experimental results end up in the standards, and then once they're in the standards, then engineers or designers, as most of you will become, would be able to look through the design standards and then calculate a reliable or safe strength. But the raw data comes normally from university test data, such as what's been published here. So here you can see the loading. So in this case here, that would be pin, and then that end here is pin. So in this case here, we're testing pin. and you can see the loading hopefully going through the centroid of the section, and then under the loading machine here you can see the instrumentation that we've put on, pin supports at both ends, and then the specimens here, the specimen, and then here we've got LVDTs to measure displacements, and then down here that shows details of the base plates. Now we've talked about imperfections, and this is so imperfections are very important. So remember that 5 millimeters for the imperfection in the example that we've just done. These days imperfection measurement is much more it's important when we try to understand the behavior of the section, that we know exactly what the imperfections are. So here we use a laser scanner. So here I've got a step motor, I've got a frame, I've got a laser scanner that goes across and back, and then we can reorientate the section. And so here this is the imperfection. So when we talk about imperfections, yes, it's nice to say it can be 1/2 sine wave, and that's a nice approximation, but in reality it's not. So for the purposes of our calculations, we would like to know exactly what the imperfection profile is. So this would be the imperfection along the section as the laser head moves along there. So we can see that these variations are in the order of about 1 millimeter. So about 1 millimeter there, about 1 millimeter there, and about 1 millimeter there. So that would be the imperfections. So we'll then do our testing, and then here we see the test results. So let's just concentrate on this one here, since the plain one isn't shown. And you can see that if that was an original column, after buckling, it's buckled outways like that, and then you can see that hole there forming a weakness there. So just to explain what we're doing, so we're testing different sections with the holes in, so that we understand the effect of the holes. And this graph here is the no hole case, so that would be the plain section. This one here is the hole case, where we put the hole, and then this one here is for a very special type of hole. So in New Zealand, they've developed what's known as an edge stiffen hole, and maybe you can see the details of it down here. You can see that it's not a hole that's been cut out by a laser or something, or a water jet. It's actually been pressed, well, it's been cut, and then it's also been pressed. So there's effectively a ring stiffener around there. So if we look at the graph here, we can see that introducing the edge stiffen hole has actually made the section stronger. So compared to the plain section. So putting in no hole has a reduced strength. Putting in a normal hole reduces the strength. This is the strength that you can read off. If you had no hole, you've got a plain section web. So this one is without any hole. And this one here, we can see that even though we have the advantages of the hole to put your surfaces through, it's actually ended up making the member stronger. So all this sort of stuff has been carefully documented and carefully tested, and then provides Australian and New Zealand design recommendations, which you can see here, so that designers operating in this country can use the test results in the design standards. This is what's known as a mathematical model. So it's a lot more complicated, of course, than what we've just done with the pi squared EI over L squared, and you would need pretty powerful computers to run this, but we've been able to discretize this into what's known as finite elements, and we can see that our finite element mode shape or failure shape is pretty similar to what we saw in the laboratory. So this is just a technique. It's just a mathematical technique known as finite element modeling, which can replace experimental test or can validate, or experimental test can be used to validate the numerical model. So that's what we do, and then once we've done there, we can use the computer simulation or the finite element model to predict what results we would have if we hadn't run some tests. So we run some tests, and then after that we may run 10 tests, and after that we may run 100 simulations of varying different things like length of hole, position of hole, etc. And then from there we can come up with some design guidance. So that, in a nutshell, basically explains how we're actually investigating bottling at the University of Auckland. And as I mentioned, this bit here is just for your background knowledge, and there's nothing here that's going to be examined.